so far whatever representation that we have seen, all the numbers they are positive in nature. So, we did not consider the negative numbers, but you see that negative numbers are quite common, like when you are doing particularly the subtraction operation. So, you can get a negative number, and that negative number also has to be stored in the computer system. For negative number storage, so we have to think about some special representation, and when we are talking about this binary number system, then these negative numbers are handled in two different ways. One representation is known as 1's complement representation, 1's complement representation, and the other representation is known as 2's complement representation. So, in 1's complement representation, so we take the complement of each of the bits to represent a negative number. For example, if I have the number, say if I have to represent the number -4, okay, in a 4-bit number system, then for first of all we take the representation of +4 in the 4-bit number system. So, +4 in 4-bit number system is represented like this 0 1 0 0. So, if you want to represent -4, then what will happen, we will complement each of the bits. So, we start complementing. So, this bit becomes 1, this is 0, this is 1 and this is 1. So, this is the -4 representation in the 1's complement number system. So, this is very good because say I can represent numbers. Okay. So, if I have got say so this most significant bit of this numbers of any number. So, if this number if the number is this bit is 0, so this represents positive number, and if the most significant bit is 1, that represents negative number. So, with that understanding, so I have got 3 bits to represent the number. So, with 3 bits I can go from say up to the number 7. So, if I have got say 4-bit representation, I can represent the number 0 to 7 that are positive, and I can take complements of them, and I can represent -1 to -8, because if I take the representation of 0 in 4-bit number system, the number is 0. So, if I take 1's complement, so this will become all 1, and that is sorry, this is -0. So, this is wrong. So, if I want to represent say +7, so +7 is represented as 0 0 1 1 1, +7 is represented as 0 1 1 1. So, if I want to represent -7, then it becomes 1 0 0 0. Similarly, if I want to represent say -7 is represented like this. So, this is not -8. So, this is going up to -7. So, I can go from 0 to +7 and -1 to -7, this is possible. However, there is a problem is that this 0 representation of 0. So, in say a 4-bit number system, 0 will be represented by this. Now, if I complement all these bits, then what will happen, it will become 1 1 1 1. That means, so what does it represent? So, as per our terminology, so this should represent -0. So, this is a problem because now you have got 2 representations of the same number, because +0 and -0, that is meaningless. So, they are same. Okay, but as far as the 1's complement representation is concerned, so you have got 2 different representations for them. So, that makes it difficult. So, because of this, so we went for another representation which is known as 2's complement representation. In 2's complement representation, what is done, after getting 1's complement representation, we add 1 to it. So, -4 in 2's complement representation will be like this. So, to get the -4 in 2's complement, first we start with the representation of +4 0 1 0 0, then we take the 1's complement, then we take the 1's complement which is 1 0 0 0, and then we add a 1 with this. So, that way it becomes 1 0 0 1. So, now you have got this this number. So, this is the 2's complement representation of minus 4, fine. Now, this 2's complement representation is, it does not suffer from this plus 0 minus 0 representation, because plus 0 is this one. So, plus 0 is represented like this, plus 0 is represented by all 0. Now, if you have got minus 0, if you try to represent a minus 0, then what we will do is that we will take this minus complement of that. So, I will get this one. Now, for 2's complement representation, with this 1 1 1 1 I will add, with this 1 1 1 1 I will add a 1, and when I do this addition, all these bits will become 0 and with a carry of 1. So, if we discard this carry, then it becomes 0. So, though both plus 0 and minus 0, they are represented by the same number, which is all 0 in the number system. So, that makes the negative number representation easy. So, there is a question of the range of numbers that you can represent. So, if you have got an n bit representation, then this 2's complement number system, so this will allow you to represent a sequence of numbers only. So, if you have got n bit representation, then this 2's complement number system tells. So, you can represent minus 2 to the power n to minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So, you can represent this range of numbers. For example, if you have got n equal to 4, okay. So, if you do not consider negative numbers, then you can represent 0 to 15, okay. That is, this 15 is nothing but 2 to the power 4 minus 1. So, you can go up to 0 to 15, but if you are representing both positive and negative numbers, then you can go from minus 2 to the power 3, that is minus 8, to 2 to the power n minus 1, that is 8 minus 1 7. So, you can go from minus 8 to plus 7. So, the rest of the numbers cannot be represented using a 2's complement number system in n bit. Okay. So, if you want to represent larger numbers, then you have to increase the value of n. So, you have to represent it using more bits in the number system. Okay. So, this way we can do this thing. Now, how does it help us is that this in 2's complement number system, the addition and subtraction, they become similar. So, how? So, how to do this? Like if I have to do this subtraction, say 55 minus say 44, okay. All these numbers are base 10 numbers, So, first of all, I have to take the binary representation of 55. So, if I for binary representation, it is easy if you just write down this chart on top, 1, 2, 4, 8, 16, as the bits, as we are proceeding towards the left, the weight of the digits are increasing. So, 30 to 55, so this bit must be 1. So, 32 is gone. So, you are left with 23. So, this 16 must be equal to 1. Okay. So, 16 23 minus 16. So, you are left with 7. So, this is 48, 32 plus 16 48. Now, I cannot take 8 because that will make it 56. So, like I have to take this 4. So, that will make us 52, and both of these should be 1. So, 1 1 0 1 1 1. So, that is the representation of 55. So, this is 55. So, for 44, again going by the same technique. So, 32 plus 8 40 plus 1 44. Now, I want to represent minus 44. So, I must have one more digit. So, if I take say a representation of 6 bit, I cannot represent 44, because with 6 bit representation I can go from minus, if you follow this formula. So, if n equal to 6, so it is it can go up to minus 2 to the power 5 to 2 to the power 5 minus 1. So, the range is minus 32 to plus 31. So, 44 minus 44 cannot be represented in this format. So, I have to go for n equal to 7. I have to go for n equal to 7. If I go for n equal to 7, so in that case I will be able to represent minus 2 to the power 6 to 2 to the power 6 minus 1. So, 2 to the power 6 is 64 to minus 64 to plus 63. So, these numbers fit in that range. So, I take a 7 bit representation, 6 bit representation, sorry 7 bit representation. So, if I want to represent minus 44, then first of all I have to, so plus 44, this is represented as 0 1 0 1 0 1 1 0 0. So, I take first 1's complement. So, that becomes 1 0 1 0 0 1 1, and then I add 1 with this. So, this becomes 0 0 1 0 1 0 1. Now, if I add this with 55, so my operation is a subtract operation, but I do an addition. So, addition how do I do? So, with this I add this number 55. So, 55 represented in 7 bit is like this, 0 first bit should be 0 1 1 0 1 1 1. Do this addition. So, it is 1 1 0, then there is a carry of 1, then 0, then 1 comes, it becomes a 0, there is a carry of 1. So, this number becomes, so this bit I can ignore. So, you see this is nothing but 11 in the decimal number, in the decimal number system, this value is 11, 8 plus 2 plus 1. So, this way I can get this addition operation done, addition and subtraction operation done in the same fashion. So, this apparently it seems what is great in it, but the point is when you are having some circuitry in your system, in your processor, then being able to do two operations done by a single piece of hardware is of much importance, because then you do not have to have separate adder, separate subtractor. Whereas, for other number system like say 1's complement number system, so you should your separate your subtraction module should be separate. So, it cannot be clubbed with the addition module. Okay. So, that way it creates some difficulty. Next, we will try to solve a few problems on this number system, some class of some problem that will illustrate how these number systems are actually used in different cases. Suppose we are the first problem that we will consider is say this one. It has got we are given two numbers in two different number systems. The base values are not known, but it is said that the numbers are same, the values of the numbers are same, then what can be the base value, fine. So, suppose the number given is the equation given is like this, 49 to the base x minus 1 is equal to 35 to the base y. So, this first number is a base x minus 1 number system, and the second number is a base y number system, and the values are same. So, we have to find out the values of x and y. What are the values of probable values of x and y? Of course, the answer may not be unique, but we can try to see what is happening. So, if this has to be true, then if we just apply our knowledge of number system. So, 4 into x minus 1 plus 9 is equal to 3 into y plus 5. So, if you simplify it further, so it gives 4x plus 5 equal to 3y plus 5. So, this 5 cancels out from two sides. So, we have got 4x equal to 3y. So, this is the requirement. So, how can this thing happen, 4x equal to 3y? Now, at the same time we can have say this thing like this x should be greater or equal 3y by 4. So, that is the final condition that turns out to be coming here. Now, this condition has to be satisfied. Now, x there is another requirement. So, so there can be many values like this equation can be satisfied by putting x equal to 3 and y equal to 4. This equation can be satisfied, but can it be a solution? This x equal to 3, y equal to 4, can it be a solution to this system? But it is not, because this x minus 1 is the base of this number system, and in this base, so what is the base now? If x equal to 3, the base becomes equal to 2. So, the allowed digits are only 0 and 1, but here I am using the digits 4 and 9. So, the x equal to 3 is not valid. Similarly, y equal to 4 is also not valid, because here it is 35. So, 5, the base 5, we have got a digit which is 5. So, base has to be more than 5. So, it cannot be equal to 4. So, this solution is incorrect solution. So, we cannot take this as the solution. So, another solution, so from this equation I can say that x minus 1 should be greater than should be greater or equal 10, because the 9 is there. So, the next digit is 10. So, from here I can say that x should be greater or equal 11. Similarly, from this I can say that y should be greater or equal 5. So, these are the additional constraints that we have over this solution. So, we have got 3 conditions now, 4x equal to 3y, this is one condition, x greater or equal 11, y greater or equal 5. So, this is the other 2 constraints. So, if you want to satisfy all these constraints, then what you get as a probable solution is x equal to 12 and y equal to say 6, sorry not 6, y equal to 16. So, we have got this solution x equal to 12 and y equal to 16. So, this way this solution it satisfies this equation 4x equal to 3y, at the same time it satisfies these requirements x minus 1 greater or equal 10 and y greater or equal 5, both the constraints are satisfied. So, this is the correct solution. Okay. So, you can have other values of x as well, like if you multiply, if you go for next higher value. So, so say x equal to say 36, any multiple of this, say x equal to, say multiply both of them by 2, say x equal to 24, y equal to 32. So, this is also a solution. So, this way there are numerous solutions, but it is one of those solutions. Okay. So, next we will go to another part of another part of this introduction lecture. So, which is about the basic digital design. So, we have seen the numbers, they can be stored in the computer system, or if the processor can process them using 2's complement number system, but for doing the processing we need to have some circuitry. So, and as I have already said that we will assume that information is available in the digital format. So, operation that is done is in the digital format only. Now, when I am talking about this digital format data and their processing, so we will be essentially talking about the digital logic circuits. Okay. So, there can be this digital logic circuit. So, there are separate courses for this. So, we will not go into much detail, but the portions that we may need while doing our discussion on this microprocessor course. So, I will just try to touch upon those concepts. Now, digital logic means, so if this is a circuit which is taken as a digital block, so it has got a number of inputs, and there can be a number of outputs. Now, unlike analog signal where the values are continuous in nature, in digital system the values are discrete, and we have got 2 discrete level. So, one is called a high logic level, and the other one is called a low logic level. So, these high and low logic levels, so they are basically 2 voltage levels that we consider, one is high, another is low. Now, there are several technologies that have been developed by in which these digital circuits are realized. 2 popular technologies are TTL and CMOS. So, these are the 2 popular technologies that we have. Now, each of these logic families, so they have got different interpretations of this high level and low level of signal. So, basically the signal that you are getting here is nothing but a voltage. Okay. So, interpretation of that voltage as logic high or 1 or logic low or 0. So, that depends on the level that the particular logic family considers. Okay. Now, in case of TTL, this logic high is taken to be anything which is more than 2.4 volt, anything that is greater than 2.4 volt, that is taken as logic high, and anything which is less than 0.5 volt, anything that is less than 0.5 volt is taken as logic low. Okay. On the other hand, for CMOS, and here the TTL family, the supply voltage, so the DC supply voltage is 5 volt. So, with respect to that, we have got this high logic level and low logic level, and this CMOS it has got the consideration, that is anything which is more than 0.33 sorry 0.3 into VDD, sorry 0.33 into VDD minus VSS. So, that is taken as logic, anything that is more than, it is less than this, anything less than this is taken as logic low. So, less than this is low, logic low, and anything which is more than 0.7 into this quantity, anything that is more than 0.7 into VDD minus VSS. So, that is taken as logic high, more than this quantity, where this VDD, VSS, so they are actually, if this is a circuit, then it will have a supply voltage. So, in case of CMOS, there are 2 points, one is called VDD and another is VSS. So, in general this VSS point is the ground point and VDD is the supply voltage point. So, that way it is similar to, we have got, say in case of TTL we normally call it VCC. So, but in this case we will call it VDD. Okay. So, this VDD and VSS, so difference between these two. So, the ground, the VSS may not be equal to 0, VSS may have some other value. So, difference between VDD and VSS, so that is taken as the difference, otherwise it is same. So, you see that there is a difference in the logic levels, and CMOS also has got various technologies, and in different technologies these VDD, VSS values they change. Okay. So, as a result we have got different as the technology scaling is progressing. So, now the supply voltage is in the range of 1 volt. So, naturally these high and low levels are much less compared to what we have in the TTL. So, of course, each of these families they have got their own advantages and disadvantages, we will not go into that, and both the families are used, though for circuit implementation it is mostly CMOS circuit, but for the output stages of the circuits many cases we go for TTL logic as well. Okay. So, looking into the digital family, any digital circuit, it can again be classified into two classes. One is called the combinational circuit class, combinational class, and the other one is the sequential class. Okay. So, combinational circuit means there is no memory. So, the circuit does not memorize its previous state. So, wherever it was, so from there it just produces the next, looking into the current input, it will produce the output. So, here output depends on current input only, output depends on current input only. Whereas, in case of sequential circuit, so output depends on current state of the system, current state plus input, it depends on both the quantities. Okay. So, it is a combinational circuit and sequential circuit. Now, for combinational circuit part, so it is generally they are realized using something called logic gates, and there are several types of logic gates that are there. So, you may be familiar with the type of logic gate like AND. So, this is a symbol of an AND logic gate, the symbol of an AND logic gate, and if I have got two inputs A and B and the output as says F. then it is represented in the form of a truth table. So, in the truth table we have got column corresponding to each of the inputs to the gate and a column corresponding to the output. Now, we list down all possible combinations of these input values. So, if it is so they can be 0 0, 0 1, 1 0 and 1 1. So, in general we will use 0 to represent the low value and 1 to represent the logic high value. Now, this AND gate says that this output should be 0, this will also be 0, in this case also it should be 0. Whenever both the inputs are 1, then only the output should be 1. So, this is the AND gate. Similarly, there are many other gates, like say there is one gate called OR gate. So, which is represented like this, A and B are the two inputs and F is the output. So, this is the OR gate, and here the truth table will be something like this. So, this is 0 0, 0 1, 1 0 and 1 1, and in case of OR gate, whenever any of the inputs is 1, so output will be 1. So, this output will be 0, but in all other cases the output is equal to 1. Another there are other gates, like we have got NAND gate, which is the invert of AND gate, okay. So, which is the invert of AND. So, in case of NAND, so if I represent this by G, then this truth table will be modified to be something like G. So, all these will be 1, and when this was giving me a 0, whenever this was giving me a 0, 1. So, in case of AND gate, so here it will give me a 0. So, that is the NAND function. Similarly, if you take the NOR gate is nothing but this is the OR gate and there is an inversion at the top of it. So, this is the NOR gate. Another very interesting gate is the XOR gate, where I have got again two input or more, or there can be more, sorry, this is not correct. So, we have got an XOR gate where say suppose we have got two inputs, and here the output will be 1 provided only one of them is equal to 1. So, this the truth table if I draw, so this A, B and F. So, this is 0 0, 0 1, 1 0 and 1 1. So, when this F is whenever, so this is 0 because both the inputs are 0, this is 1, this is 1, but this is again 0, 1 1 is again 0, telling that the inputs are same. This XOR gate, it has got a very important application when we are going into this microprocessor designs, like because you see it can compare between two inputs A and B. So, if you are trying to check whether two inputs are same or not, then this XOR gate is the straightaway the answer. So, this is you can take the XOR of the two numbers or two inputs, and if the answer is 0, that means they are same. If the answer is 1, that means the values are not same. So, that way XOR gate has got very good application. So, other gates, similarly you can have XNOR gate as well, where at the XOR gate output you take a bubble. So, if this is the XOR gate, you take a bubble here. So, that is the XNOR gate. Okay. And of course, another gate that we did not talk about explicitly is the inverter. So, which is a single input single output circuit. So, inverter means whatever be the input, the output will be the invert of that.